up to 0.0000000000002%. So while particles are not really points, by treating them as if they were, we get a pretty good picture of the universe. Not only did this idea advance science, it also led to a lot of real-world technology we use every day. But there's a huge problem: gravity. In quantum mechanics, all physical forces are carried by certain particles. But according to Einstein's general relativity, gravity is not a force like the others in the universe. If the universe is a play, particles are the actors, but gravity is the stage. To put it simply, gravity is a theory of geometry, the geometry of space-time itself, of distances which we need to describe with absolute precision. But since there is no way to precisely measure things in the quantum world, our story of gravity doesn't work with our story of quantum physics. When physicists tried to add gravity to the story by inventing a new particle, their mathematics broke down. And this is a big problem. If we could marry gravity to quantum physics and the Standard Model, we would have the theory of everything. So very smart people came up with a new story. They asked, what is more complex than a point? A line or a string? String theory was born. What makes string theory so elegant is that it describes many different elementary particles as different modes of vibration of the string. Just like a violin string vibrating differently can give you a lot of different notes, a string can give you different particles. Most importantly, this includes gravity. String theory promised to unify all fundamental forces of the universe. This caused enormous excitement and hype. String theory quickly graduated to a possible theory of everything. Unfortunately, string theory comes with a lot of strings attached. Much of the maths involving a consistent string theory does not work in our universe with its 3 spatial and 1 temporal dimensions. String theory requires 10 dimensions to work out. So string theorists did calculations in model universes, and then try to get rid of the 6 additional dimensions and describe our own universe. But so far, nobody has succeeded, and no prediction of string theory has been proven in an experiment. So string theory did not reveal the nature of our universe. One could argue that in this case, string theory really isn't useful at all. Science is all about experiments and predictions. If we can't do those, why should we bother with strings? It really is all about how we use it. Physics is based on maths. 2 + 2 makes 4. This is true no matter how you feel about it. And the maths in string theory does work out. That's why string theory is still useful. Imagine that you want to build a cruise ship, but you only have blueprints for a small rowing boat. There are plenty of differences: the engine, the materials, the scale. But both things are fundamentally the same: things that float. So by studying the rowing boat blueprints, you might still learn something about how to build a cruise ship eventually. With string theory, we can try to answer some questions about quantum gravity that have been puzzling physicists for decades, such as how black holes work or the information paradox. String theory may point us in the right direction. When used in this spirit, string theory becomes a precious tool for theoretical physicists and help them discover new aspects of the quantum world and some beautiful mathematics. So maybe the story of string theory is not the theory of everything. But just like the story of the point particle, it may be an extremely useful story. We don't yet know what the true nature of reality is, but we'll keep coming up with stories to try and find out until one day, hopefully, we do know.